log periodic dipole array series on antennas and wave propagation, lecture number 4.14. Log periodic dipole array is an antenna capable of working in several bands. Hence, it is a multi-band antenna. It is also capable of exhibiting large bandwidth. Hence, it is a broadband antenna. In addition, its operating frequency can also be varied over a large range. Hence, it is also a frequency independent antenna. As the name suggests, it is an array of dipoles. In the present session, we discuss about its structural features, principle of working, radiation characteristics, applications, and also several other interesting aspects pertaining to this antenna. Let us begin the session by considering a few basics pertaining to this antenna. A log periodic antenna, LP antenna, is a multi-element directional narrow beam antenna that operates over a broad band of frequencies. These were invented by Dwight E. Isbell, Raymond Duhamel, and its variants by Paul Mays. The functioning of these antennas is based on one principle, Ramsay's principle. According to Ramsay's principle, a structure which could be defined entirely by angles without any characteristic length dimension should have characteristics that are frequency independent, Fi. In short, if structure is defined, specified entirely by angles, the antenna exhibits frequency independent characteristics. It says impedance and pattern properties will be frequency independent if the antenna shape is specified only in terms of angles. This is Ramsay's principle. A remarkable property of the successful frequency independent antennas is size of the effective radiating aperture automatically adjusts or scales with frequency to produce an antenna that has the same pattern and impedance at all frequencies. So scaling with frequency, adjusting with frequency is an important property of these antennas. Some more basics. A true Fi antenna, frequency independent antenna, is physically fixed in size and operates on an instantaneous basis over a wide bandwidth with a relatively constant impedance, constant pattern, constant polarization, and constant gain. So this constant is common to impedance, pattern, polarization, and gain. It remains same. Duhamel in 1957 proposed by means of appropriately located discontinuities in the angular structures of Ramsay, it is possible to achieve frequency independent operation. For these antennas, pattern and impedance properties get periodically repeated with the frequency when plotted on a logarithmic scale. Basic principle of a frequency independent antennas is Ramsay. Duhamel suggested an amendment in which he allowed discontinuities in the angular structures of Ramsay. With the discontinuities, pattern and impedance get periodically repeated with frequency when plotted on logarithmic scale. The graph for input impedance SWR or pattern against log of frequency consists of periodic, identical, but not necessarily sinusoidal cyclical variations. Hence, these structures are called log periodic antennas. These two slides second one and the third one, they give us the background for naming these antennas as log periodic antennas. The LP metal sheet antennas are limited by mechanical considerations to microwave frequencies, but LP dipole array wire antennas function successfully even into important HF band. So dipole array wire antennas, they can be operated even below microwave range into HF band. A particular form of the log periodic design, the log periodic dipole array or LPDA in short, log periodic dipole array, introduced by Isbell, is often used in VHF band television antennas. The basic concept is a gradually expanding periodic structure array radiates most effectively when the array elements, here dipoles, they are near resonance. In these antennas with a change in frequency, active or radiating region moves along the array. The log periodic design looks very similar to Aggie antenna, but is very different electric. LPDA and Aggies are often combined in television antennas that cover both VHF and UHF. From a distance, it is very difficult to differentiate LPDA from Aggie. They look very much similar, but when it comes to their electrical behavior features, they are totally different. Of course, they can be combined into an antenna to cover VHF and UHF television reception. A few points regarding structure of a log periodic antenna. A log periodic antenna, LP, it is also known as log periodic array, log periodic aerial, aerial antenna. These are synonyms. Log periodic antenna, log periodic aerial, both means same. It is an array, hence it is called a log periodic array. It is a multi-element directional antenna designed to operate over a wide band of frequencies. It was invented by John Dunleavy in 1952. The most common form of log periodic antenna is log periodic dipole array or LPDA. The LPDA consists of a number of half-wave dipole driven elements of gradually increasing length, each consisting of a pair of metal rods. The dipoles are mounted close together in a line connected in parallel to the feed line with the alternating phase. Electrically, it simulates a series of two or three element Agioda antennas connected together, each set tuned to a different frequency. In this slide, a good amount of information regarding the historical background of a log periodic dipole array. It is given along with the structural features. Some more information regarding structural features of LPDA, log periodic dipole array. The structure consists of an array of dipoles. It is already mentioned with lengths and spacings arranged in a log periodic manner. This has to be kept in mind. Lengths vary in a log periodic manner. Spacings vary in a log periodic manner. The length of each element is a function of the desired frequency response. For broadband reception, this leads to a series of ever shorter dipoles towards the front of the antenna. The relationship between the lengths is a function which is called geometric ratio. The ever decreasing lengths makes the LPDA look, when viewed from top like a triangle or arrow with the tip pointed towards the transmitter. The elements are spaced at intervals following a logarithmic function of the frequency known as spacing factor sigma. We are going to see tau and sigma, geometric ratio tau, spacing factor sigma. These are important parameters pertaining to LPDAs. Some more information regarding structure. Tau and sigma are the key design elements of the LPDA design. The elements are excited by a uniform two-wire line with the line transposed between adjacent dipoles. Notice transposition is implemented in feeding the LPDA. The antenna may be fed with a balanced line connected to the feed point or coaxial line entering from the right and passing through and inside one of the balanced lines to the feed point. Here, some information regarding the feeding of the antenna is provided. A common design method uses two booms, each one acting as a transmission line, and mounting the dipoles on alternate booms. Here is shown a pictorial diagram of dipole array, LP dipole array. Tau, geometric ratio. It is ln by ln plus 1. This is ln plus 1. Rn plus 1. This is Rn. This will be Rn plus 1. Dn plus 1. This is Dn. Naturally, this will be Dn plus 1. Sn plus 1. Spacing factor sigma. Sigma is Rn plus 1 minus Rn by 2 ln plus 1. In this diagram, transmission line and its transposition, it is not shown here. Here is one parameter alpha. This is also an important parameter alpha. The general configuration of a log periodic array is described in terms of three parameters: geometric ratio, included angle, spacing. Geometric ratio, its symbol is tau, it is always less than 1. By definition, it is the ratio ln2, ln plus 1, rn2, rn plus 1, dn2, dn plus 1, sn2, sn plus 1. These ratios are equal, where ln's are dipole lengths, rn's are distances between feed and dipoles, dn's are distances between dipoles, sn's are gap spacings at dipole centers. Typical range of tau is 0.95 to 0.7. Included angle alpha, some important points regarding included angle. It is half of the angle made by straight lines through the dipole ends meet. Its typical range is 10 degrees to 45 degrees. There is a relation between values of tau and alpha. As alpha increases, corresponding values of tau decreases and vice versa. Increase in alpha leads to decrease in tau and vice versa. Larger values of alpha or smaller values of tau result in more compact designs, which require smaller number of elements separated by larger distances, whereas smaller values of alpha or larger values of tau require closely spaced large number of elements. This is an important aspect. Spacing factor sigma, it is always less than 1. Sigma is already, it was introduced. It is the ratio of Rn plus 1 minus Rn by 2 ln plus 1. These three parameters are related in the general configuration of log periodic array through alpha is included angle, tau is geometric ratio, and spacing factor is sigma is spacing factor. Alpha is tan inverse 1 minus tau over 4 sigma. Now we are slowly moving to the functioning of the antenna. Electrically, the structure can be divided into three regions: transmission line region, active region, reflection. When the array is working, the total array can be divided into three parts: transmission line region, active region, reflection. What are their properties? First, we consider transmission line region. Its the salient features are: antenna elements are short compared with the resonant length. Length is small, very small compared to lambda by 2, and their impedance is capacitive and relatively high. Second feature, the element spacing is small in wavelengths, and phase reversal introduced by transposition of the transmission line means that adjacent elements are nearly 180 degrees out of phase. Each element current leads the preceding element current approximately by alpha equal to pi minus beta d. 3. Radiation from this region is small in the backfire direction. Backfire means like this is backfire. Now active region, its salient features are: 1. The element lengths approach the resonant length L, but is slightly less than lambda by 2, and their impedance has an appreciable resistive component. 2. The element spacing is sufficiently large that the phase of the current in a given element leads that in the preceding element by an angle alpha equal to pi minus beta d, which may approximate to pi by 2 radian. Third feature, important feature, this region produces a strong radiation in the backfire direction. Now third region, reflection region, its features are: 1. In this region, the element lengths are greater than the resonant length, more than or equal to lambda by 2, and the element impedance becomes inductive. Second feature, important one, the element spacing may be larger than lambda by 4, but the phase shift per unit length along the line in this region is small. Third feature, the radiation, if present, is small and it is in backfire. Notice radiation is in backfire direction. Here is shown the interconnection between parameters tau, sigma, alpha. Here is also shown a line, optimum design line. Over this line, certain numbers are there: 8.5, 8, 7.5, 7, 6. These numbers indicate gain in dBi. The purpose of this particular diagram is, if you want, let us say, an array that exhibits a gain of 8 dBi, then what should be alpha, what should be sigma, what should be tau? All that information one can read from this particular diagram. So it is highly useful for a design engineer. Certain design relations are provided here in this one. The bandwidth of the system determines the length of the smallest and the largest elements of the structure. Bandwidth of the active region BAR are related to alpha and tau by, according to Carroll, BAR is equal to 1.1 plus 7.7 multiplied by 1 minus tau whole square cot alpha. The bandwidth of active region, it is related to alpha and tau by this relation. In practice, a slightly larger bandwidth BS is usually considered for design than that which is required. The two are related by BS is B into BAR, which is B into 1.1 plus 7.7 1 minus tau whole square cot alpha. The total length of the structure L from shortest L minimum to longest L max element is given by this. L, capital L, is lambda max by 4 multiplied by 1 minus 1 over Bs cot alpha, where lambda max is 2L max, which is equal to V by F. V is velocity. 3. From geometry, the number of elements are determined by this form: 1 plus natural logarithm Bs over natural logarithm 1 over tau. A few points regarding opening. At a wavelength, radiation occurs from the middle portion where the dipole elements are approximately lambda by 2 long. When wavelength is increased, the radiation zone moves to the right, and when wavelength is decreased, it moves to the left with the maximum radiation towards the apex or feed point of the array. So at any given frequency, only a fraction of the antenna is used where the dipoles are about lambda by 2. This gives beautiful information regarding the functioning of log periodic dipole array. Now, certain information regarding directivity and impedance of these antennas. Impedance, radiation characteristic, and directivity of this antenna are 1. The radiation characteristics of the log periodic dipole array are functions of array geometry as expressed by factor tau and angle alpha. 2. The radiation is in backfire direction, linearly polarized beam of the apex with electric vector parallel to the transverse elements. 3. The input impedance can be made to have any value from 50 to 200 ohms. It depends mainly on the characteristic impedance of the transmission feeding the element. 4. The gain ranges from 7.5 to 12 dB over an isotropic radiator, it means dBi. With the larger gain values achievable with the smaller angles of alpha, that is with the longer arrays. A few points regarding applications. It is used mainly in the field of high frequency communications where multi-band steerable or fixed antennas are required. It is more efficient than the rhombic antenna because there is no terminating resistor absorbing the power, and hence it is preferred. It is also used for television reception with one antenna for all channels. It should be strictly noted that it is not the log periodic shape that provides broadband property for antennas. It is due to its self-complementary nature that gives always a constant input impedance equal to 60 pi 188.4 ohms independent of frequency and its shape. With this, we come to end of the session. In this session, Ramsey's principle, which is basic, fundamental behind the design and functioning of log periodic antenna. It is introduced, a small brief is given in which the historical development process of log periodic arrays are developed. Principle of working, structural features, functioning, applications, all are explained. Hope this session is useful to you. We meet again in another session with a new topic very soon.